Right. Let's look at intramolecular force and the potential energy that's associated with it. Intramolecular forces are the bonding that goes through it. So this is looking at atoms or ions that are bonding to each other, not intermolecular forces, which are between molecules. So all of chemistry is based on positives and negatives attracting. You have atoms, which you think of as neutral, they're not charged. So you think, well, how can they attract each other? Well, they're both comprised of things that are positive and negative, electrons and protons. So at a big distance, there really is no attraction, which means there's no potential energy of the fact of wanting to change that to kinetic energy. They're kind of so far away. However, as they get closer, just to randomly decrease the distance by a half, there's going to be an increase, or I should say a decrease in the potential energy, which means now they're going to be less likely to be going anywhere else. When we get to 74, which happens to be the observed bond distance, we have the lowest energy. So this is the most stable form of two hydrogen atoms in, I could say, in a space, let's call it. Now, this distance is dictated by what's positive and what's attracting. So at all of these areas, you have attracting forces bringing them together and repelling forces pushing them apart. However, at the observed bond distance, they're going to be equal, roughly, because then they actually just vibrate back and forth until something else comes along. If you try to push them closer together, that's going to decrease the radius and therefore increase the increase the repelling forces of the same charged nuclei or same charged electron clouds, and therefore push it apart, therefore being at a higher potential energy. Much like so that if you push this so far, it'd have enough repelling force to overcome any attractive that if you were to like release it, it'd go boing and spring apart and go across the screen. There's a nice little FET that kind of shows that, just kind of silly. Ionic bonding is in a similar fashion with Coulomb's law, but it works kind of in a different manner based upon the ideas of the size of the bond lengths. So when they're really close, remember this is like very small distances, there's a lot of repulsive interactions because there's still a lot of protons in here and electrons for that matter. And we also see that there's attractive interactions because, again, the whole thing is positively charged and the whole thing is negatively charged. And at some point, there's a bond length that's going to be a good length for them to have that attraction and repulsion come out. And it looks a little bit that the energy is that based upon these kind of countering out. What happens, though, is that we have a much higher amount of energy per mole than we do with the covalent compounds. And you might see that this radius is 236 when it was 74 on the other one. So a lot bigger charges, a lot more energy because of the fact that you have full charges as opposed to these partial charges that we found in electrons and protons. But likewise, with Coulomb's law, as they get further apart, that amount of energy and attractive interactions really decreases down to essentially zero. Now, these types of graphs are likely to show up in different places on your AP exam. They just like showing these diagrams and having you explain a little bit. So get used to talking about them and the idea of potential energy and how it increases as things get too close together, decreases when you get to the bond length, and then will increase again once you get too far away. Now, another good place that this will come up with is values. Now, this is looking at energies and lengths covalent only. So looking at the connections, and Coulomb's law, I think I had it on a previous slide as being over R. It's R squared. So that change in distance really magnifies since it's squared rather than just being linear, I guess would be R. So if you take any one of these things here and look at a carbon-carbon length, you get a double bond, it's closer together, triple bond even closer. We look at that same connection over here. So much energy per moles, gets bigger. So what makes more sense is that as the closer they get, the more energy is needed, or the more energy it has together and stored up, which makes sense that the energy is related to our Coulomb's law, and that the closer they are, the same, that the bigger the energy is, because again, carbon and carbon is still the same thing, so that doesn't change your Q1 and Q2 for any one of these. What changes is your length. So that'll make a difference in the idea of how much bond energy is needed. Now you might remember back a little bit, gotta click on this one to go back, that as things got further away, these ions got further away, they have a higher potential energy than when they're closer. And this negative refers to a release of energy. It's no longer stored. So if we were to think all individual ions being separate, that means it has a really high potential energy. And when they come together, that's going to lower the potential energy, therefore releasing energy to the surroundings. So this is called this lattice energy. And it's going from things at a gaseous form to a solid, because that's really the only way you can talk about ions being as far apart as possible is when they're in gaseous form. And it is weird to think of metals as a gas, but you get them hot enough, they'll get there. So when you're trying to predict what will occur or the difference in those lattice energies, well, it's the size that makes the biggest difference. Because the overall charges are going to be 1 to 1, 1 to 1, 1 to 1, 1 to 1, 1 to 2. Those are going to be consistent when you just replace one of equal ion size. So think about Coulomb's law again. Again, radius makes a difference, but also charge can. When it comes to heat being released, the larger negative value means more energy released. So lithium chloride releases more energy per mole than cesium chloride. And calcium oxide, you can see, is way more than sodium fluoride. So in taking a look at the values, you see that lithium chloride has the shortest bond distance, which makes sense that we have the biggest lattice energy, very similar to covalent. The biggest bond energy is going to have the least amount of lattice energy. Biggest bond length would have the least amount of lattice energy stored. Calcium oxide, we see, okay, it's 239. It's about the same size as lithium chloride as far as size. But look how much larger it is. And that comes from the idea of the charges are much larger. This is 1 to 1. That's 2 to 2, which means this would be 4 times what you'd kind of expect this to be, which, hey, that looks pretty close. So it's about 4 times the size because it's about 4 times the charge. Likewise, you have sodium and fluoride that you have here, about the same size, but it's 4 times as less, roughly, due to the fact that this radius is also less. So there's a very good connection with the idea of Coulomb's law and the energy values for ionic and covalent. So again, in summary, the shorter the length, the more energy, whether it be lattice energy with ionic compounds or bond energy with covalent compounds. But size makes the biggest difference. Another addition over here with ionic is charge. So when you have bigger charges, like 2 to 2 as opposed to 1 to 1, you're going to get much more energy as well. Let me know what kind of questions you have. I'm here to help, and let's get going.